So Nick, I could have easily interviewed you about the first topic in the class, which is big telescopes and adaptive optics and so on, but we're talking about astrobiology. How did you get interested or drawn to astrobiology?
Well, I started very much the same way that you did. You go into physics because you want to understand how everything works, and you think, well, little things build up to big things, so if I understand the smallest things, I'll understand what's happening in physics. But after a while in physics, I got the sense that, no, I was seeing it, but I wasn't really understanding something new. And astronomy seemed so exciting that I moved into that. And obviously by seeing the very big, I was going to understand everything because it included everything. And
right.
After a while, it still wasn't quite getting it right, and eventually it sort of pushed me along bit by bit. I was studying water, and then I was studying rock dust, and then I was studying how do you look for life elsewhere. And I started asking what life was, and by then I'd become an astrobiologist without quite realizing it. And I was finally invited to join the team for making the next roadmap on astrobiology, and we came up with the topic of what is life. And the person who was leading the effort said, we can't touch that, it will cause so much controversy that we have to leave it alone. And I said, this is absolutely ridiculous. Here we are looking for life and we don't know what it is we're looking for. It doesn't make sense.
Right.
And so I started trying to make sense of it myself, and eventually I feel I have some kind of sense of what it is. And it all comes through a letter that Darwin wrote in the last couple of months of his life when he was talking about what life is. He said there's a principle of continuity between the physical sciences and life. And there is a principle of continuity between everything that humans learn. We really ought to have just one language because we're talking about the same things, and they have to be able to be described in the terms of the other disciplines. So what life is a topic that ought to be describable in physics. And then you say, well, what is life? And it's got this aspect of choice about it. And choice is a word physicists look at and they say, no, that's not mine, that's social science. But there has to be the physical equivalence of choice, and there has to be a process where you step from seeing that a billiard ball bounces this way and moves off in such and such a direction, and that is its kind of choice, to understanding that I come to your office and I talk to you, and that is another kind of choice. But there is a sequence that leads from what the billiard ball does to what I'm doing, and there have to be classes of things that you can discuss that are intermediate, so that whereas it's easy to talk about what a billiard ball does, when you come to discuss what a forest fire does or a hurricane does, you say, well, it's as though it's got a mind of its own. It doesn't have a mind, it has a history. And it has a history that's been built in because of the things that have happened in the past. And that will in part determine what it does in the future. But it stops having a great complexity in its history simply because it has to be simple. The parts that go together to make up a fire or to go together to make up a hurricane are really rather simple. They don't have much choice because of the way that chemical link, the way that atoms join to one another. And they join to one another relatively simply, except for one peculiar element, carbon. And carbon has a great variety in the ways that it is linked, so much so that when we look at all the molecules that we can see in space, there are more carbon-connected molecules than there are of all the other kinds put together. And that is the basic stuff that comes into choice. But there's one other part. I want to talk about water. Water has another aspect of choice. If you have molecules that have the ability to electrically connect, they're called polar, and you put such molecules into water, they just join and go with it. If you put other kinds of atoms, like those molecules, those that make up oil, for example, into water, then they won't mix with it. They'll stay apart. And if you take a molecule half one and half the other, it will sit right on the edge of water with the part that likes to be in water into the water and the part that likes to be away. There's a real example of choice for you. 3 different things that can happen. Mm-hmm. And the combination of those 2 things, the behavior of carbon and the behavior of water, have created this rather remarkable possibility, this stuff we call life.
Right, and we do view those as 2 basic ingredients. But returning to definitions yes. are not always useful, I guess. But I've seen spectrum of definitions of life where when they get very specific and crunchy and concrete, they adhere so closely to the one example of life we know on this planet that they might not be relevant to any other example. And yet if they back off to being very general, then to me they imply things that might not even be recognizable elsewhere. So how do we deal with that spectrum of definitions, or find the right place that's productive?
Well, we have to find the right place, and I believe that choice is this element that is for us the necessary intermediary, the way that we can start considering the development of what we are from the materials. But the other aspect that is important is the concept of continuity. Supposing we start considering that ape-like ancestor of both us and chimpanzees, and we say, did it survive? Mm-hmm. The answer is yes. It actually survived in 3 species, 2 of which are the 2 different forms of chimpanzees, and the other of which is us. Mm-hmm. But that survival, therefore, was rather different from the way that we think of ourselves as continuing, because it's continuing but with change. And that aspect of change has been a huge part of the difference. So if we ask, well, will humans survive? We have to realize that when we're asking it, we're not asking whether the future will contain creatures that are just like us, but whether it will contain something to which we have contributed in a very special way. And that, again, gives us a feeling that life includes more than just what we have right here now, but has other possibilities that can come in, and equally that we have to consider other ways that it could have arisen. But the peculiarity, the thing that is different about life, is that it has a variety of responses. That's the thing. If we look at something black on a piece of paper, I push on it and say, will it move? Or I try various other things. I look to see what kinds of responses it has, what kinds of choices it will make. And if I see it has choices, I tend to say it's alive. And if I don't see it has choices, I say it's dead, throw it in the trash can.
Right.
So that is, to me, the real distinction.
So with that as a basis of continuity and change, which is, I agree, we see all around us in biology at every scale, one of the big issues, and still I guess unknowns, is how did it start? And it's historical science, so I guess we may never know the answer. What are the best thoughts on that kind of dotted line between macromolecules and the first cell? Do we have any good ideas?
Well, the remarkable thing is the stuff that we see in places where stars are forming are some of the nearest things to living materials that we can find. And I remember having a discussion with one colleague, and he said, there's this crazy stuff. It's got this string of carbon atoms, and then right at the end there's a nitrogen. He said, we find that in space. Where's that in life? And the answer is, well, you've got these strings of carbon atoms, but they occur in a rather different form. They occur as the boundaries of cells, and there are certain subtle differences, but if you start thinking about how these things will interact chemically with water and so on, you will see that they will tend to create these kinds of substances rather like the stuff on the boundary of cells. And there are other things, amino acids, which are nitrogen compounds that are also part of us. They make up proteins, and again there's a huge amount of discussion about formation of carbon compounds, but the nitrogen has turned out to be absolutely crucial. And if you let the carbon come to Earth and burn, do whatever else it's going to be done, you will separate the carbon from the nitrogen, and you'll have great difficulty on Earth linking it up again, because we are what's called an oxidizing environment, and we've been mildly oxidizing since the beginning. And the nitrogen needs to stay with the carbon to make those, and that the stuff that comes in does indeed have the carbon linked to nitrogen. So I think it's much more likely that the stuff that came in that was the basis of life, rather than the stuff that came here and then it did something.
And you've alluded to a number of ways in which the basic ingredients have a proclivity, if you like, for doing something complicated and interesting.
Yes.
So is the corollary of that you would expect this to have, biology to occur on most of the physical situations, all these Earth-like worlds that we're finding with the same ingredients, the same physical
I would have liked to, but I found one problem, and that is a rare element, phosphorus. And when you ask how phosphorus got into life, it's one of the hardest things to explain.
Which you need for ATP. So energy storage.
You need it because it energizes life. And so you have to get it and get it energized. And the way it seems to have got energized on Earth is that phosphorus comes out of volcanoes as part of volcanic dust, and it is already energized. And if that dust gets to things, it can indeed energize them and start some of the processes going. So if you ask me, are the ingredients there for life, for example, on the moons of Saturn, I'd say there's a good chance that the carbon's there, the nitrogen's there, the water is there in the form of ice and sometimes even squirting out. But the thing that I would worry about there is the phosphorus. Is there a process that will energize it and put it there to get the process operating?
Now, is this an intriguing connection that we think that life could have started in volcanic, subterranean, subaqueous environments?
Oh, yes.
Where there's those kind of chemicals are available dynamically?
Yes, of course.
And so we can imagine that's a common process. And I understand in the exoplanet world, people have argued about whether a geologically active planet is a predicate for life. That if it's geologically dead, it's likely to be biologically dead as well.
I don't know whether that is true, because phosphorus needs to be activated at the start. But one of the relatively early developments of life was to find ways of activating it without that, to use light or heat or chemical processes, and they have been able to take over. And so if you find a place that is geologically dead but is exposed to sunlight, it could have transferred all those processes into using sunlight to energize phosphorus. So that would not necessarily mean that it has stayed dead. It would have to have had, I think, something like volcanic activity to get started, but not necessarily to be maintained. And for example, Mars, we don't think that there's much in the way of geological activity on Mars today, and we would tend to call it geologically dead even if it's marginally still alive. But if life had formed at that time and had managed to switch over to using light to energize the processes, then indeed it could be that we'd find life on Mars.
So I want to explore a word that comes up in the discussion of life and how it started and so on, metabolism. How should we understand, how should we think about that issue?
Okay. Yes, there's two words that have great difficulty. One of them is metabolism and the other is reproduction. And they are both used in a very special sense by biologists who don't like to have them used outside that sense. But if you're going to see a principle of continuity, you've got to take both metabolism and reproduction out of biology and use them elsewhere, or at least say that there are processes that come from the physical sciences that link up, and at some point biologists are prepared to call them metabolism and reproduction. And metabolism is just a chemical process of some kind, and it's used often to pick up those processes which require energy. But that's only one of the things. That's where you build and you need energy to drive building, but equally there are metabolic processes that break down and produce energy, and it's just that you have to have processes going on in life simply because if you're going to survive, you have to replace that which is being broken off or lost in some other way.
And go on to talk about reproduction. What are the issues with that concept?
Yes, reproduction is even trickier because people like to think that reproduction produces copies. However, think of it this way: if life had started off making exact copies, it would never have changed.
Right.
It would never have evolved to produce us. It's because it doesn't make exact copies that it has a chance to do these wonderful things. So there is a process of making inexact copies which had to have started off before there was life. And when you get asked about inexact copies, there are all kinds of things that make inexact copies, and you tend to say, well, okay, so it's inexact. But if you get chemicals that are approximately copying, then they can start to do things, and you can then build into higher and higher levels of copying that allow you to make greater and greater structures. And we use this concept of complex structures before. We need complex structures to get many of the things to happen, but we have to build up that complexity. And we build up that complexity by some things managing to work and the majority of things don't manage to work. And as a result, there's this continuous process, if you will, of choice that has chosen one direction which is going to survive or chosen another direction which is not going to survive. And then at the end of it, we have life, and we start looking at it and say, it's improbable that this could ever have existed. How is it that we have all of these things in sequence that are there, and the probability of them coming together at random is zilch? It's like having a Boeing airplane built by a hurricane passing through a junk yard, and it doesn't happen.
Was Hoyle one who used that
Hoyle came up with that, and the answer is it occurred bit by bit. Every choice was part of it, and if you think of a choice as one of two, then you have a series of choices, and by the time you've made 3 choices, you're up to a probability of 1/8, and then another 3, and you're 1/64th, and another 3, and suddenly you realize you're down the road talking about hundreds, thousands, millions, and billions in improbability. The improbability of life existing is that we managed to kill off all the other alternatives, and so these are the things that are left.
So that's an interesting issue, the one you started with, the fact that, perfect in a chemical situation, perfect fidelity in coughing ends up being sterile in a
Yes.
sense, but imperfect coughing leads to possibilities and multiplies up very nicely.
Yes.
And some external sculpting of the environment will winnow out things that are more interesting or less interesting.
Yes.
Let me address another not vexatious, but sort of a concept that can be taken different ways by biologists and non-biologists. Yes. Information storage. How should we think of information in life? Because we think of biology as coding information in some way.
Okay.
What are the crucial elements if we're generalizing life?
The first one I talked about were these things like hurricanes and forest fires, which have very, very little information storage in them. They can be, the wind can be rotating at such and such a speed or pulled some way, but there's very, very little information in there, and it doesn't stay. If you once can start off on this process with carbon and water and nitrogen, you started to build in some complexity, and that complexity then, if it helps survival, has the possibility of opening up and creating further and further layers of complexity.
Right.
Now,
but complexity per se doesn't connote
no.
information.
So let me come down to it. So here is a microbe, and it's going along, and it encounters something. As a result of the genetic structure of the microbe, that which has been built into it, it will respond in a very particular way to that. That will result in it either living or dying. And you can say that the information that contributed to it living was indeed this genetic information. But that's only one kind of information. And it's rather similar to the kind of information that occurs in plants, but they are capable of something more complex than that. And if you start asking, for example, how a Venus flytrap will actually capture a fly, you discover that there is a considerably complex amount of information that has to go into that process, but it's all genetic information. If flies were to change abruptly so that they no longer settle on that kind of plant, it would die. It wouldn't be able to modify except perhaps by a genetic accident.
Right.
Now we developed another kind of life form that we call animal life, and animal life includes flies and worms and all these other snails and so on as well, but they all have a nervous system, and the nervous system means that they actually check on an environment by responses, and their nervous system then does a comparison with something that has been built into it, whether it's been built into it genetically or by parents acting on it in some way, will vary with the species, but there is a different kind of information that has developed there, and you can have two of this same species that were trained differently somehow, and they will respond differently. And all the way up through animal life, so that, for example, you will find very intelligent dogs or cats or elephants or whatever. But they lack one thing that we've got. We have got information storage, books, computers, and all the writings and so on, and we have a communications system of speech, so we can transfer information to one another, and the way that I will choose to do something could depend on how my genes came out, how my parents taught me, how my life experiences affect me, how I've learned something from the internet. All of these things can be put together, and I will weigh it up and I will make my decision as to what I'm going to do. So we are different from ordinary animal life. We have suddenly become something that is totally new, that is capable of making its decisions, its survival decisions, based on a huge amount of information that has been gathered from the past and present.
Right. So let me get back to that, the branching point where you started to talk about animal life and so
Yes.
on. So microbiologists, of course, famously will say, you know, the things we study are just as complex as you know, humans. There's just there can be as much genetic information in a worm as in a human. So it's another business of connecting complexity
Yes. Well,
and the genetic information with the functioning of the organism. Do you think it was a fluke? I mean, do you think this contingency in evolution makes us a fluke?
If you look at evolution, the path that led to animals was one of eating, eating living material. And eating living material also implied the possibility of being eaten by other living material, and those put a priority on decision making. And so as the capabilities of eating expanded, the capabilities of learning how to survive had to expand with them, and this process of matching patterns of what is the pattern of what I'm seeing and how does it relate to what to be afraid of in the past, or what I've been told is likely good food, is tested all the time.
And yet, if there's a selective advantage to that, it did take quite a long time to happen, you know.
It took an incredible amount of time to happen. Part of it was the problem of getting together the pieces that could do this. It involved taking something that was capable of engulfing on one hand, and something else that was capable of complex chemical processing. And there were some microbes, archaea, that did the engulfing part, and another kind of microbes which are rather like E. coli, which are great chemical factories, but they can't engulf. And one of those got engulfed at one point, and instead of being eaten, it managed to survive and work with the system, and then the whole thing started changing as a result of that. But it took a while for it to go, and there was a huge amount of development that was necessary. But there were two parts to that, and there were two crucial stages in the development of the Earth that made it possible. And the first was at around 2.4 billion years ago, there was a dramatic ice age. And in that
this is an early snowball, right?
The early snowball. And as a result of that, there was a process that ended the ice age and put a huge amount of oxygen into the atmosphere, because there was this wonderful, warm, moist environment for green microbes to grow. Then that ended, and so, but it hadn't really put in terribly much oxygen into the atmosphere. And oxygen is crucial because it is a very dangerous material for the outsides of cells, and they avoid it very well by sticking themselves together and making multicellular organisms. So oxygen drives multicellularity, and you had to wait for another of these snowball Earth events to come along, and it came along just before the Cambrian Revolution, just when animal life took off and plant life all had their beginning with that sudden arising of oxygen and the need for cells to stick together to make multicellular organisms, and they developed a capability at that point of specializing. The chemical complexity that had come in through those mitochondria suddenly allowed the development of a variety of cells that could do different things, and they were essential for animal life to start going into these things, to develop spinal cords, and then bony structures, and then you had 4 bony structures on a coelacanth-like fish, and it managed to start walking around on the rocks, and the whole process took off.
So to paraphrase and use in a different context another Darwin quote, the warm little pond, I mean, these are dynamic and stressful events that actually led to great innovation in biology.
You have to, yes. if it doesn't kill you, there's a
Right.
chance that it can do something good for you.
We should be reading Nietzsche rather than Darwin. Yeah. So now this is for people who look at the history of life on Earth, and then they look back from our pinnacle of evolution,
Yes.
supposedly, and you understand the temptation of teleology and purpose and so on is so strong when you look at this. Can we really describe this chronology and ascribe it to sort of unguided forces and purely natural events? Do we know enough to how to explain the whole chronology to be confident of that?
We do not understand why the laws of physics are the way that they are, and we certainly don't understand everything that happens on Earth. So to say that it happened without any guidance is to go beyond what we really know. What we can say is that with those laws, it's not very surprising that we've got to where we are, because there is this tendency for complexity to build up if it can be advantageous, and it has built up to a point where it has developed a totally different kind of development through us. Electronics and printed books are both things that are not biological entities. They're post-biological entities. We have suddenly been able to carry the aspects of life back into this inanimate world and use the fact that we can create complexity to put complexity into materials like stone and so on.
So in a sense, you would say, even though we haven't managed to manipulate genetics in a detailed way, we have transcended biology already.
Oh yes, I would say that. And
it's hard to imagine it hasn't happened somewhere else in a galaxy with 100 million habitable worlds.
Our Earth only started 4.5 billion years ago, and definitely twice as long ago as that, and maybe back quite a bit further, the possibility of planets coming up with this kind of chemical material must have existed. The question is, can one go through the next phase? Because what you've done is you've taken creatures that are getting their resources by killing. And we kill and eat.
And when there were only a few million of us, no problem. You didn't run out of anything.
Well, that's right, except we kept watching the big animals die off, and the trees were cut down, and places like Charco were no longer livable. It is part of the problem that we've got, that we are like that. And what we've got to now make is a transformation where instead of killing one another, we're actually going to cooperate. And that's a non-trivial transition. And the big question is whether we can or can't make it. If we can make it, we have a chance of going on to something absolutely incredible, whereby things go out into the universe carrying information. I don't think it's mainly by radio waves. I think that the amount of information that is needed is so great compared to what you can send with a radio signal. You're probably going to make little physical things and send them.
Right.
It's the way of getting a lot of information to a specific place with the least resources and the fastest time.
So since you've alluded to it, I'll ask a question about SETI. I mean, do you think it's well motivated and we should absolutely do it, or do you think it's hopelessly anthropocentric, or is it what's your feeling on SETI?
Well, you're asking whether 200 years ago we should have been looking for smoke signals. And the answer is no, because you really have to look for a way in which a large amount of information can be sent. However, if information is sent in that way, there will be a need to also send a beacon signal to indicate where to go and when to go, how to go and look for it. So it is quite likely that there is indeed some radio communication involved in this process as well. That's with the science we know. Whether there's something beyond radio, we don't know yet. So it's worth looking.
You said 200 years ago we'd be trying to communicate with smoke signals. I presume in maybe only 50 years we'll be using gravity waves because we've got them figured out, and it'll be a whole different regime.
This is part of the problem. If you try and imagine Leonardo da Vinci being brought today into this room and asked, you try to talk to him and you discover that almost everything that you want to talk about doesn't make sense to him.
Right.
And he was the smartest guy around at his time.
And he knew about all subjects.
It's only 500 years ago.
Yeah, right.
And if it changes that fast, then it's almost hopeless to go that way. On the other hand, if you don't try, you'll never find it. And the best hope we've got, until we've learnt more, are radio waves. So we look with radio waves. I think it's a reasonable thing to do. On the other hand, I wouldn't bet a great deal on its success.
Right. So let me ask a hypothetical about that alludes to the likelihood of life in the universe. Say you had the 100 Earth clones, as close as you can imagine, just hypothetically. They all started with a sun-like star, 10 billion years ago or whatever. First issue of habitability. I mean, they all have the ingredients,
Yes.
Do you think you would expect microbial life or life of any kind on few of them, none of them, most of them? Is that part a fluke, or what?
I would expect microbial life to develop relatively easily, though maybe it's only one on average one planet per system, because you've got to get together some things that, like water that comes in from the cold, and you've got to have phosphorus that takes the heat. So it's a bit of a juggling act. But on the other hand, 100 planetary systems, I would say the chances of some of them generating microbial life would seem to me relatively high.
Now, what about the Stephen J. Let me just pause a minute.
Sure.
Hey. Oh. Thanks. We're nearly finishing. Now the Stephen Jay Gould hypothetical, that you had the 100 Earths and you came back in 4 or 5 billion years. Would you be surprised? Would you expect complex, advanced life on a few or many? Are the contingencies and possibility, so uncertain that we just simply don't know?
One of the things that has driven these snowball Earth events is continental drift, and it occurs slowly, and it managed to produce just 2 of these snowball event groups in our history. I don't know what the probability is of producing a couple, and I suspect it takes a couple in general, but that could be low or it could be high. If it's reasonably high, then I would say it's rather likely that complex life would have developed. But then you ask the further question, if it had gone to advanced life like ours and used up most of the easily available resources on Earth and then died out because it couldn't manage to cooperate, would we find intelligent life there? Because all those easily available resources have gone, the chances of it recovering and getting a second chance is, I think, very slight. I think you get one crack at going through and changing from competition to cooperation.
And of course, you're homing in on the fact that in the Drake equation, with sort of plausible and partially determined numbers, for the first factors, you end up with sort of n equals L, which is Frank Drake's license plate. So this L is the critical thing. And are you pessimistic or sanguine about L based on our example? Because that's all we have.
I think that we are smart enough to be able to understand that it's this or nothing, and I think it's possible to get the majority of people to understand that there is meaningful life in cooperation rather than competition.
Mm-hmm.
And once you get the majority over to that opinion, they're going to do something. They're not going to let the others wreck the opportunity.
Mm-hmm.
So I think I'm hopeful.
Mm-hmm. That's good. And then just the last question, astrobiology is just moving at a breakneck pace, with especially the exoplanets and the Kepler and so on. You're pretty confident we're going to find at least microbial life somewhere else in a decade or so? I mean, is that a good bet?
The time scale is horrible. If you look at the history of NASA, everything takes about 5 times longer than you would have hoped. And so although we thought up schemes for detecting life on planets more than 20 years ago, that the chance of actually building one of those has seemed to decrease with time rather than increase. Mm-hmm. So it's going to take quite a while. If you start talking about by 2050, I would tend to agree with you. I don't think it's going to come fast.
Okay, which is somewhat of a frustration for the people in the field, because their field appeals to the public too. I mean, most people can get excited about that research agenda.
It's all part of the extent to which we can work with cooperation rather than fighting one another. And if we started cooperating a bit more and fighting a bit less, we'd find that there were more resources available for that kind of activity.
Yes, okay, good point. That's a good point to finish on. Thank you, Nick.
Fine.